Valence bond theory merges Lewis structures with the idea of atomic orbitals, 2s, 3p, 3d, etc. Lewis theory says that covalent bonding occurs when atoms share electrons. Well, valence bond theory says that covalent bonding occurs when valence orbitals of adjacent atoms overlap. Then, two electrons of opposite spin, one from each atom, combine to form a bond. So, in valence bond theory, there has to be orbital overlap, and each of those orbitals needs to contain only a single electron. Thus, when they overlap, they will have two electrons, and those two electrons will form a bond. So, valence bond theory is like Velcro. No overlap, no bond. So let's consider a few different molecules. I'm going to start by drawing out the orbital diagram for hydrogen and at least the end of it for chlorine. And you can see that for each of these atoms, they have one orbital that has only a single electron. And so what's going to happen, according to valence bond theory, whenever these atoms form bonds, these orbitals are going to overlap with other orbitals that also only have a single electron, and then that overlap will result in a bond. In hydrogen, we can see the unpaired electron is in the 1s orbital, and in chlorine, the unpaired electron is in the 3p orbital. There's a hydrogen atom there with a 1s orbital, and there's a single electron in it. And then another hydrogen atom has a 1s orbital with a single electron in it. And where those orbitals overlap, according to valence bond theory, that's responsible for the bond. What about for Cl2? There's a 3p orbital from one chlorine atom, and there's a 3p orbital from another chlorine atom. Each of those 3p orbitals has a single electron, and now there are two electrons that are shared, and that, according to valence bond theory, makes the bond. How about hydrogen chloride? We're not talking hydrochloric acid here, we're talking hydrogen chloride. There's the orbital from hydrogen that has a single electron. There's the orbital from the chlorine atom that has a single electron. When they overlap, there are two electrons, and there is thus a bond between those two. There is always an optimum distance between two bonded nuclei. At this optimum distance, attractive and repulsive forces balance. If we think of the distance between two bonded nuclei as something along the lines of a mass on a spring, if we take those two nuclei and we try and push them closer together, they don't really like that. The repulsive forces will begin to become larger and will tend to push them back. On the other hand, if we try and pull those two nuclei further from each other, then they don't particularly like that either, and the attractive forces will tend to kick in to bring it back to equilibrium. Kind of like this mass on a spring. If it's just hanging from the spring at rest, that's the equilibrium position. If we then push the mass up and let it go, then spontaneously the mass will fall back down, and of course it will oscillate until it reaches that lower down equilibrium position. Or if you grab the mass and pull it below its equilibrium position and then let it go, it's going to pop back up and oscillate until it comes back to equilibrium. In other words, there's always an optimum distance, not just for the position of a mass hanging from a spring, but for between two nuclei. And that optimum distance is where the minimum potential energy exists in the system. You might call it the Goldilocks distance. Too close, no good. Too far away, no good. Something in between where the potential energy is minimized, just right. Let's summarize valence bond theory. Valence bond theory says that a covalent bond between two atoms forms when one valence orbital from each atom, each containing a single electron, overlap, after which the two electrons form a bond. The distance between bonded nuclei is the distance at which the potential energy of their interacting charges is minimized.